All right, so as you can see, students will be finding some vertical asymptotes, and we'll also be looking for something called removable discontinuity for our rational functions. Now, at this point, I've shown you guys how to find a vertical asymptote and a horizontal asymptote. So let me start with vertical asymptote. We've already talked about this. We can look at the table and determine what the vertical asymptote is. The question is how, or what do we look for? All right, so what do we look for in a table when we're talking about a vertical asymptote? We're looking for what? The error. You can find the error in the table, and you can find your vertical asymptote. Of course, you can also look at the graph, which is what we did over there in the lab yesterday. Look at the graph to find the vertical asymptote. But you can also do one other thing, and that's what we did a couple of days ago. What was the other thing we could do to find the vertical asymptote? All right, take the denominator, make it equal to 0, and solve. So those are three different ways that we can find the vertical asymptote. Yesterday we talked about horizontal asymptote. How do we find the horizontal asymptote? We can look at the graph. That's one way. What was the other? The degrees. The degree in the numerator, degree in the denominator. What if the degrees are exactly the same? The numerator and denominator exponents are the same. Divide the leading coefficients. All right, so it's y equals the leading coefficients divided by each other. All right, what about if the exponent is larger in the numerator than it is in the denominator? The degree is higher in the numerator. Remember what that one was? All right, let's take a look at our notes real quick. Notes from yesterday. There were three things. What if the degree is higher in the numerator? Higher degrees in the numerator. What does it say in the notes? What's that? No horizontal asymptote. All right, so if you said that, you are correct. No horizontal asymptote. If the degree is larger in the denominator, then of course that one was the y equals 0. Now notice here it says today we're going to be finding vertical asymptotes, which we should already know how to do. And we're also going to be looking for something called removable discontinuity. We'll talk about what that is here in a second. All right, let's get started here. Now notice up at the top it says sometimes expressions might appear to be equivalent, but maybe not. We need to make sure. So the question is, how can you tell for sure if two rational expressions are equivalent to each other? Well, they give us an example here. We've got our first rational expression, 1 over x plus 2, and our second rational expression, x over x squared plus 2x. The question is, are these equivalent? Well, there's a couple of different ways that we can determine whether they're equivalent to each other or not. Here's the first one. Number 1, show that the two functions above are equivalent by factoring and simplifying the second rational expression. So let's take a look at the second one, x over x squared plus 2x. Go ahead and write that down for me, because we're going to factor it, and then we're going to simplify. So here we go. Numerator. Numerator cannot be factored, so we'll leave it as x. The denominator can be factored. There's a GCF there, and that GCF is a what? X. So let's factor out the x. So since x is the greatest common factor, what are we going to multiply that x with to get x squared plus 2x? What goes in parentheses? X plus 2. X plus 2. So I've just factored my denominator. Now I can come over here and cancel out those common factors, which in this case are these x's here. So what am I going to be left with when I simplify this? 1 over x plus 2. So notice when I simplify this, I get exactly the same thing I had over here. So they're equivalent, and I can show that using these factoring and simplifying. All right, now let's take a look at the second one, number 2. On number 2, they want us to generate a table for each of these functions. So I'm going to need you to go to your calculators, and in y1, we're going to type in the first rational expression, 1 over x plus 2. Now make sure when you type it in, guys, you go ahead and type it in as a fraction. I showed you the other day. Use the alpha key and then y equals. Your numerator is 1, denominator is x plus 2. That's going to go into y1. Then go down to y2 and type in the second rational expression or equation, x over x squared plus 2x. Once you get them both in, you're going to take a look at the table. look at the table. And in that table, you'll see an x column and two y columns. And that's because we have two different equations. So we're going to get both y columns filled in. So here we go. Next to 2, or actually negative 2. What do you see next to negative 2? What are the two? Error in y1. What about in y2? Error. So you see an error and an error next to negative 2. What do you see next to negative 1? 1 and 1. What do you see next to 0? 1/2 and error. What do you see next to 1? 1/3 and 1/3. And next to the 2, you should see a 1/4 and 1/4. Now, something strange just happened here. Now, if they're the same or they're equivalent to each other, the tables should be identical. However, look right below it. It says, in what way are the tables not equivalent? What do you notice here? What's that? Y2 has an error next to what? 0. Okay, write that down for me over here. Y2, or the second rational expression, has an error next to 0. Let's stop and think here. We just talked about this. The errors represent what? The vertical asymptote. So if we look at the first equation that we typed in, it has one error, which means we have how many vertical asymptotes? 1. Look at the second equation. Second y. Notice it has 2 errors. So how many vertical asymptotes should I have? 2. We talked about that the other day, right? And why are there 2 on this one, but only 1 on this one? What's the difference between the equations? Look at the denominators. Yeah, the second one has an x squared. That's a quadratic. And a quadratic has 2 solutions. Okay, so we're getting 2 errors because we have a quadratic in that second equation. So, from the looks of it, I should have 1 vertical asymptote on the first equation and 2 vertical asymptotes in the second equation. That's what it looks like, right? But is that the case? Let's take a look. Go to your graph now and sketch me a graph of what you see on your calculator. Sketch a graph of what you see on your calculator. Remember, you still have both of your equations in there. So that graph you're looking at does represent both equations, both graphs. All right, so let's see, the graph looks a little, and this is just a sketch, guys, it doesn't have to be. All right, so the graph looks something like this right here. Is that the same graph you're getting? All right, let's take a look at this graph. A second ago from the table, we said the first equation should have 1 vertical asymptote, the other should have 2 vertical asymptotes. Well, notice here. How many vertical asymptotes does it have? How many vertical asymptotes do you see there? 1. Write that down for me. There's only 1. Does this match the information given in the table? Well, it depends on what equation we're talking about, right? If we look at y1, then yes, it matches up. But if we look at y2, y2 had 2 errors. Therefore, according to y2, we should have 2 vertical asymptotes. So does this match up with the information in the table? No, not for y2. Not for y2. Because if I look at y2, the second equation should have 2 vertical asymptotes. But as you can see here, there's only 1. There's only 1 vertical asymptote. So what's going on here? Something fishy is going on. We're going to find out here in a second. We'll get to the bottom. Let's keep going though. Take a look at the next equation they give us. Y equals x squared minus 3x all over 2x minus 6. Now notice here we're going to find the vertical asymptote, but this time we're going to find the vertical asymptote by taking our denominator, setting it equal to 0, and solve it. So this was another technique we had for getting our vertical asymptote. So let's solve for x. First, I'm going to add 6. 0 plus 6 is 6. Then I'm going to divide by 2. So 6 divided by 2 is 3. So my vertical asymptote here should be a 3. Put that in your calculator and let's get the table. And let's see if this is adding up here. If I'm saying the vertical asymptote is at 3, when I put this in my calculator and look at the table, I should get what next to the 3? An error. Let's see if that happens when I put this in the calculator. We should see an error next to 3. That's what we just said. The vertical asymptote is 3. All right, so let's go ahead and fill out the table. Next to 0, you have a what? 0. Next to 1 is 1/2. Next to 2 is 1. Next to 3 is error. And next to 4 is 2. All right, so does the table support the location of the vertical asymptote found in number 4? Remember, number 4, we just got through saying that the vertical asymptote was going to be at 3. Does that show up in the table? Yes. So yes. If I'm saying the vertical asymptote is at 3, then I should be looking at a error next to 3 in the table, which is exactly what I see here. All right, let's take this one step further, and let's take a look at number 6. What they want us to do is sketch a graph of the function given in this window. So go ahead and change your window for me. Our window for the x values are going to be x minimum is negative 9.4, x maximum is 9.4. Make sure you're using a scale of 1. The y minimum and maximum are going to be negative 6.2 and positive 6.2. Once you have your window adjusted, sketch the graph that you see on your calculator on your handout. All right, let me see what kind of graph. So if I put in right. Is everybody getting that right there? All right, that is correct. You should be getting a line. What is strange about this graph? Okay, number 1, it's linear. It's a line. That's one thing that's strange about it. It's linear. Well, what else is strange about it? What did we just get through saying we should have? We should have a vertical asymptote. Where should that vertical asymptote be? At 3. Do you see a vertical asymptote at 3? No. So write that down for me. There's no vertical asymptote at 3. We just took the denominator, set it equal to 0, solved it, got 3. We even went to our table. We saw an error next to 3. So all the indicators say that we should have a vertical asymptote at 3. Yet, we don't see a vertical asymptote. So what the heck is going on here? Why are we not seeing a vertical asymptote at 3? All right, so let's see why is it that we don't see a vertical asymptote at 3. Okay, over on the back. Over on the back. Notice up at the top it says usually. Usually. Values of x to make the denominator equal to 0 will create a vertical asymptote. Which is why we set our denominator equal to 0. So that we can find that vertical asymptote. But again, they stress the word usually. Usually that's the case. Unless that value makes the numerator equal to 0 also. So if I take that same number that makes my denominator equal to 0, and it also makes my numerator equal to 0, then this creates something called a removable discontinuity. Removable discontinuity. So they give us an example over here. Notice the rational equation they give us is x squared minus 3x over x squared minus 2x minus 3. So here's what they've done. They factored both the numerator and the denominator. And if we focus here on the denominator, right there, the denominator, you'll notice we have two factors. If I set the first factor equal to 0, I end up with a negative 1. If I take the second factor, set it equal to 0, I should get a 3. So at first glance, it should look like it should show two vertical asymptotes, one at negative 1 and one at positive 3. But that's not the case. Right? Notice what we get instead at 3 is not a vertical asymptote, but instead we get a hole. Instead, we get a hole. Put that in your calculator for me. Type in x squared minus 3x over x squared minus 2x minus 3. Take a look at the graph. Is this the same graph you're getting on your calculators? Kind of, sort of. Do you see a vertical asymptote at the negative 1? Is there going to be a vertical asymptote there? Do you see a hole at positive 3 on your graph there? You see it? All right, so good. Now, we need to be real careful because if you're not really paying attention, you may miss that removable discontinuity. You got to be really keeping your eye on that. Now, there's still a vertical asymptote. It's just that we also have this removable discontinuity. So what we're going to be working on today is how do you find or how do you distinguish between the two? So here's what we need. If you plug in an x value and you get a numerator over 0, then we're going to let that be our vertical asymptote, or that's going to be our vertical asymptote. But if you plug in an x value and get 0 over 0, then what you have instead is a removable discontinuity. You're going to get that hole instead. Now notice out to the side it says that the table will show us an error. And when we see those errors, we're going to think that they're vertical asymptotes. And we're not going to know for sure whether it's a vertical asymptote or that removable discontinuity until we do some factoring that. Okay? So right over here, you don't know for sure until you factor. This is how we can be for certain whether we're looking at a removable discontinuity or a vertical asymptote. All right, so let's go ahead and take a look at some examples and see how this is going to work. Here's our first one. This is our first one. All right, so what we're going to do is we're going to see what our vertical asymptote is and what our RD is. And what does RD stand for? Removable discontinuity. All right, so here's how we're going to do it. We're going to take the denominator, and we're going to factor it out. So let's factor. Actually, you know what? We're going to do both. Factor the numerator and the denominator. It'll be easy. Let's start with the numerator. Let's factor the numerator. X squared plus 6x plus 8. Well, to get the x squared, I know I can multiply x times x. Now I need factors of 8 that are going to add up to 6. What are some factors of 8 that add up to 6? 4 and 2. All right, so we've just factored the numerator. Now let's go ahead and factor the denominator. Again, x times x will give me x squared. What are some factors of negative 6 that are going to add up to a negative 1? Negative what? Negative 3 and positive 2. So I've just factored as much as I could. Factor the numerator, factor the denominator. All right, so now what I'm going to do is I'm going to take the factors in my denominator, and I'm going to set them equal to 0 and solve, just like we were doing the other day to find the vertical asymptotes. So if I take the first factor, set it equal to 0, x minus 3 equals 0. If I solve that, I end up with a 3. If I take the other factor, set it equal to 0, subtract 2, I get a negative 2. So right now it looks like I have a vertical asymptote at 3 and a vertical asymptote at negative 2. However, that's not the case. One of those actually represents the removable discontinuity. The question is, which one is it? Anybody want to take a guess? Negative 2. That is right. So the removable discontinuity is negative 2. The vertical asymptote is the x equals 3. How do we know this? Why is it the negative 2 is a removable discontinuity? Look what happens when you plug in negative 2 for your denominator, you get a 0. But notice when you plug in that negative 2 here in the numerator, what's going to happen there? You're also going to get a 0. And 0 over 0, remember we said that was going to be our removable discontinuity. So really, here's the key, guys. Point that out. Notice how they share a common factor. This is going to be important here in a second. We're just looking for the common factor. Let's try that again. Number 2, let's factor the numerator first. X times x is x squared. What are the factors of negative 8 that are going to add up to positive 7? 8 and negative 1. Okay, so those are the factors of our numerator. Let's go to the denominator, do the same thing. Factor it out. X times x will give me the x squared. Now I need some factors of 4 that are going to add up to a negative 5. What are those? Negative 4 and negative 1. Those are the factors. Okay, at this point I factor the numerator and the denominator. So let's look at the denominator. I'm going to take each one of the factors. I'm going to set it equal to 0. And I'm going to solve. So if I solve the first one, I'm going to end up with a 4. Take the second one, solve it, I get a 1. Now again, at first glance, it looks like both of these are the vertical asymptotes. But that's not true. One of those actually represents the removable discontinuity. Which one is it? X equals 1. X equals 1 is our removable discontinuity. X equals 4 is the vertical asymptote. And it's very easy to spot because right here you'll notice that they share a common factor. All right, let's go to number 3. Again, I'm factoring the numerator first, so there's a GCF there, and that GCF is a 2. So if 2 is the GCF, what would go in the parentheses? X minus 5. We just factored the numerator. Now let's factor the denominator. X times x is x squared. We need to know what are some factors of negative 5 that are going to add up to a negative 4. Negative 5 plus 1. So those are the factors of the denominator. Now that you have it factored out, take your denominators, take those factors in the denominators, set them equal to 0, and solve. So the first one ends up being x equals to a 5. The other one over here equals to a negative 1. But again, one of these is the vertical asymptote. One of them represents the removable discontinuity. So which one's which? Let's see. Which one is the removable discontinuity? X equals what? 5. And we know that because right over here we notice they share a common factor, which means x equals to the negative 1 would be our vertical asymptote. All right, I want you to try the other 3 for me. Try the other 3.